Hi, my name is Ricardo Ruiz, ID A01383658, and this is my explanation of the code from the Melee Challenge number 3. So basically, first off, to comprehend the movement of our robot, we need to look at the equations that we're given. So basically, here we have three first-order differential equations, which represent a kinematic model. So basically, here we have in the first equation, in the x, the first equation represents basically the robot's position on the x-axis. So here basically v represents the linear velocity of the robot, and the cosine represents the change on it projects the velocity on the x-axis. And similar with the y component, so we have that the linear velocity is represented by v, and the sine of theta is the orientation depending to determine the y component of our system. And the last one, theta, so basically here it defines the change of the orientation, and well, it's basically the angular velocity that we're gonna have. So well, basically these three equations are from a kinematic model, which means that they're gonna move the robot only from one place to another without considering any other factors like forces, masses, and inertia. And well, there, as I mentioned, it's only from one place to another, so we need to make a model that fills out or smoothens the trajectory from one point to another. So for this, we're gonna use a Euler's equation. So with this, we're gonna just like simulate like a continuous model on the computer, and well, it's gonna use integration to do so. So here we have the equations that represent the linear velocity and the angular velocity. But well, we need to consider that our drive system or the robot is gonna move with two wheels. So these equations represent the relationship between the linear and the angular velocity. So this basically will mean that, well, if both wheels are spinning at the same ratio, it will make the robot move straight forward, and if one is faster than the other one, it's going to result in the robot to turn. So these equations are what are going to represent that relationship. So well, basically these are all the equations that we're given to make our model. So to summarize, only we have the three kinematic model equations and the framework for the velocity and the wheel speeds. So now let's see my ROS model and my code. So here's a brief explanation of my code. I am using screenshots since my computer can handle the screen recording while having ROS opened. So basically here we're gonna have our libraries, including NumPy and, well, for the quaternions and the structure from the float32 and the conversions and the autometry. So basically we're gonna start by declaring the variables. So these ones are gonna be one for each one of the differential equations. So it's gonna be the position in the x-axis, in the y-axis, and of theta, the velocity, the omega, and, well, the wheel radius and the wheelbase, which were already established values. So this is gonna be for it to start everything at 0, and then depending on the key that we're pressing, they will change. But well, then we're gonna declare the messages that we're gonna use. So we have the post-TF transfer stamp and the autumn messages autometry, which well, basically here it is created for broadcasting the robot's transformation, and, well, in the TF3. And, well, the autometry message, it encapsulates the position and the velocity information, and, well, these messages they're gonna be critical for the inter-node communication from our ROS. Then we're gonna have the initialization of the post TF from the position X, the position Y, and the position of theta. And we're gonna declare which one is going to be the header and which is going to be the child. So here basically the parent frame is going to be autumn and the child is going to be baselink, and these configurations will be the reference frames for all of the subsequent position updates. Then we're gonna have our callback, which we're listening to the incoming velocity commands from the topic, which is cmd_vel, which we're gonna see later on. But basically, when a new command arrives, we update the global variables from velocity and the omega, and this will represent the forward or the rotation of the speeds, and the movement of the speeds. Then we're gonna have our main loop, which basically in our main block we are initializing our Rust node, which is called b1 sim, and we're starting the position and the orientation, which is the position in x, the y, and theta, and all three of them, the initial position is going to be 0. Then we're going to put the rate at 200 Hz so we can ensure a high frequency update, so we can see it as smooth as possible. And well, we're going to register our shutdown command and initialize our transform, which is from up, and our subscribers and our publishers, which are gonna be given by the publisher of the autometry, which is given by the topic autumn, from the structure autometry, and the queue size of 10, which the queue size is the amount of values that it is saving. So it is basically well, yes, it's saving the values for the use. So depending on the queue size that you put, is gonna be the number of values that it is gonna save for further working, basically. And well, for the left wheel and right wheel, we're gonna use the structure of float 32, also with the queue size of 10, so it can save some data in the transitioning from one point to another. So it has values in which it can smoothen the transition from the kinematic equation from one place to another. And well, basically here we're gonna just declare that the transform broadcaster and the left wheel and right wheel messages, that we're gonna make them equivalent to our float 32 structure, which will be published afterwards. So basically here we're just determining the structure from the float 32. Then on our while loop, we're gonna have again, we're gonna determine, this is gonna be the cycle that is gonna follow. So this is the main loop. We're gonna be integrating here the Euler's equation for the smoothing from the kinematic equations, and we're gonna define them also. So basically here we're gonna put dt, which is gonna be the time step between each one of them. So this is gonna help us integrate the differential equations and use Euler for the smoothing. So basically we're gonna have the position in x, which is given by the linear velocity times the cosine of theta times our time step. Same for y, the linear velocity times the sine of the position in theta times the time step. And for theta, the position in theta is gonna be equal to our omega times the time step. And well, here we're gonna initialize our transformation messages, which basically after we update the pose, we are gonna convert the orientation of the angle into a quaternion. So this will help us make that transition from one point to another without any singularities or moving directly. And well, basically here we're just defining the translation from the position in x is going to be equal to our equation, which is given here, and our position in y, the translation in y is going to be equal to the differential equation also given. And in theta we're not going to use them, so we're going to establish them as 0, and then for the rotation we need to add the x, y, z, and w for each one of them. So as you can see here, q is given by the equation from the quaternion from Euler, which uh, which will have one for each frame, so X, Y, W, and Z. And then we're gonna transform our send our transform, which is gonna be the pose TF, and we're gonna have our autometry sent, which here basically we're gonna build the autometry message, which includes the robot's position, as I mentioned earlier, and the orientation, which again will be translated into a quaternion from Euler. And as you can see here, we have the orientation also in X, Y, Z, and W, and it's also going to be equal to the differential equations defined earlier, so it knows where to apply the changes and how to apply them. And well, it will represent the measurements, and basically here at the end we're just adding these covariances, which we're gonna put at 0, which will basically, these are for more complex navigation systems, and we're not gonna use them, so we're gonna establish them at 0. And finally, here we're gonna have the equations for our velocity commands. So here we're gonna transform the high-level velocity commands into individual wheel speeds given by the variables from the right wheel and the left wheel, and we're gonna calculate the angular velocities from each one of them. So this will ensure if the robot is gonna go straight, is gonna turn. So if one is gonna go faster than the other. And finally, we're gonna have these the wheel speeds are translated into packages, into messages, and they are published by WR and WL. And for the float32 to work, we're gonna have to put these published messages. So this, if you remember earlier, we have here the float32 defined for the pop right wheel and pop left wheel. So that is the same that we're gonna use for declaring the publishing. So we're gonna publish that messages, which is given also by the package saved on the data from the equation, from the equivalency from the right wheel, which is the equation from the angular velocity. So that is gonna contain the information from the packages. So here is the code working. So the libraries and everything that I explained earlier. And well, we're gonna run it using the launch file. So here we put the launch file. And we're gonna have our robot. So basically, to see the float32 messages from the speeds from the left wheel and the right wheel, we're gonna use this ROS topic echo, which are gonna show the position, the velocity of each one. So same for the left wheel. And basically here, when we give him some, for example, here it's gonna have one wheel spinning faster than the other one. So as we can see, the right wheel should be faster than the left wheel. And as we can see, it is working. Then if we give it a straightforward direction, it should be the same number. So 8 for the right wheel and 8 for the left wheel. And well, here is gonna, there's our robot. And well, we can control it with the keyboard. And the data of the float32 messages.